Hi gents, I hope you've had a really amazing Easter break and are ready and raring to go with the continuation of our work on thermal energy. We have already covered specific heat capacity and specific latent heat, but we haven't yet done the practicals that are required in the course. So both of the lessons this week are going to be on doing those practicals. The first lesson is going to be on specific latent heat and the second lesson is going to be on specific heat capacity. So I thought we'd just start by recapping what we mean by specific latent heat. If you remember, we've already covered the different states of matter, so solids, liquids and gases, but when we are moving from one state to another, we require energy. We need energy to break those bonds, and that's what latent heat is. Latent heat is the energy required to change a substance from one state to another. The word specific adds an extra aspect to that definition because it's per kilogram. So the specific latent heat is the energy required to change 1 kilogram of a substance from one state to another. Now I've got in brackets here at constant temperature. It isn't really part of the definition, but it has come up in past papers in the past where we have had to add that statement in to get all the marks. So just to avoid any kind of doubt, always try and add in to your definition of specific latent heat the at constant temperature at the end. Okay, so we've got two different types of specific latent heat. We've got the specific latent heat of fusion. That is the transition from a solid to a liquid or a liquid to a solid, so either way. And the other one is the specific latent heat of vaporization, and that's the transition from a liquid to a gas or from a gas to a liquid. There will be others for sublimation and for ionization, but they're not on our course. However, these two very definitely are. We need to know the difference between the two. The other thing that we've already covered is the formula. So the formula is L is equal to E over M. E and M are energy and mass respectively. So energy is measured in joules and mass is measured in kilograms. And L is the specific latent heat. And as I'm hoping most of you can see, that's going to be measured in joules per kilogram. So this is a graph that you should now be familiar with. We have temperature on the y-axis and energy on the x-axis. We have 5 very distinct regions. We'll start with the 3 that are at diagonals. This is when the substance is in 3 different states: solid, liquids and gases. It's the sections in between that I want to concentrate on now. So we've got 2 of those. The one down at the bottom, so this one down here, that is the specific latent heat of fusion, and this section up here is the specific latent heat of vaporization. Clearly, just as a recap, we can see that the specific latent heat of vaporization is much bigger than the specific latent heat of fusion because we need to break more bonds. More work needs to be done in changing a substance from a liquid to a gas than it does from a solid to a liquid, because we need to break more of those bonds. So what we're going to do in today's lesson is we're actually going to try and reproduce a section of this graph. So this section here we are going to try and reproduce for ice. Okay, so what we're going to do is we're going to melt some ice and reproduce this graph. So if we go on to our next slide. So this is how we're going to do it. We have an energy meter connected to a cell and an immersion heater. So that's how we're going to provide our energy. We're going to use this immersion heater submerged into some ice. We're also going to need a thermometer to measure the temperature. One of the really important things is to stir this continuously. You'll see when Dr. Cook does this in the video that you're going to watch that he is continually stirring to ensure that we've got an even distribution of that ice, of that temperature throughout the ice. It would be a good idea to get this diagram into your notes along with your results and graph. So this is the graph that you should get from Dr. Cook's experiment. It looks something very similar. There might be some deviation, but it's kind of the gist of what it is going to be the same. And you're going to have to use this graph to determine the specific latent heat of fusion of ice. So I just wanted to run through with you very quickly how you're going to do that. So one of the key things is this value here, so the value at which the temperature starts to rise. You can see that the temperatures remain stable from 0 all the way up to, in this case, 4.9 kilojoules. Now, because of errors in the thermometer. Your line might not necessarily run exactly along zero. It might be slightly above or slightly below, but you'll very clearly be able to see when the temperature starts to rise. So the other thing that you're going to see from the video is Dr. Cook actually measuring the mass of the liquid that he has melted. So it's important that you take a note of that mass, because we're going to need it in order to work out the specific latent heat. So how do we do that? Well, we use the equation L is equal to E over M. The energy that we provided is the energy that we take from this part of our graph, and the mass is the energy, the mass that Dr. Cook records on the balance at the end of the video. So we need to substitute those values in. Now it's important to note that our graph has a scale in kilojoules, and so I haven't put 4.9 into my formula. I've actually put 4,900. Likewise, the mass was measured in grams, but I've not put the value into our formula in grams. I put it in kilograms. So 120 grams is 0.12 kilograms. And then all I have to do is plug those into a calculator, and I get out my value of 40,800 joules per kilogram. Now, your values are going to be nowhere near this, nothing like this at all. These are just some values I've made up to give you an example of the kind of calculation you're going to have to do. So you need to repeat this using your own graph that you've plotted from the data that Dr. Cook has provided in his video, and you are going to have to then do this calculation yourself. And on to specific heat capacity. Again, we're going to start with a recap. So when we're talking about the heat capacity of an object, we're talking about the amount of energy required to change its temperature by 1 degree Celsius. Obviously, we've got the word specific here. So again, like with the specific latent heat, the specific heat capacity is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. So objects with a high specific heat capacity are going to have to gain lots of energy in order to change their temperature by 1 degree Celsius, and therefore take much longer to heat up. And obviously the reverse could be said for when objects are losing energy and therefore cooling down. So something like water has a very high specific heat capacity, takes a very, very long time to heat up, and a very, very long time to cool down, because it needs to give out or gain lots of energy before the temperature changes by 1 degree Celsius. The formula that we've already covered is E is equal to mc delta T. If you remember, sometimes I write that as E is equal to mc theta. You need to be familiar with seeing it in both formats, and each of those terms, so E stands for the energy measured in joules, M for mass measured in kilograms, delta T change in temperature in degrees Celsius, and the specific heat capacity is the C, which is measured in joules per kilogram degrees Celsius. Just take note of the brackets around the kilogram degrees Celsius. It is very important. So on to the experiment we're going to do in our second lesson. So this is on specific heat capacity. So the setup is very, very similar to the one that we saw with the specific latent heat. This time, rather than melting ice, we're going to be heating up an aluminium block. Now that aluminium block has been machined to make sure that it is exactly 1 kilogram. Just makes the experiment a little bit easier when it comes to our analysis. So again, we've got an energy meter to measure the amount of energy that our immersion heater is going to be providing into that aluminium block, and we've got a thermometer to measure its temperature. So after you've watched Dr. Cook's video on the specific heat capacity experiment, you need to plot yourself this graph. We've got temperature on the y-axis and energy in kilojoules on the x-axis. When you plot your graph, you should get something that looks a bit like this. Now, you might have a curve down at this bottom end because of the fact that the heater needs to heat up. So some of the energy that's being provided isn't going into the aluminium block, it's actually going into the heater itself. And you might also get a curve up at this end because of the fact that as we start reaching higher temperatures, that aluminium block starts giving out energy to the surroundings. And so not all of the energy that we're providing is actually going into the aluminium block. Some of it's going into the surrounding air. What we're going to concentrate on is the straight section in the center. So how do we link this back to our equation and kind of work out the specific heat capacity of our aluminium? Well, let's look at the gradient of the graph. We calculate a gradient by doing rise over run. Now in this case, the rise, so what's our change in the y-axis is actually a change in temperature, and the run is the change in energy. And so our rise over run becomes delta T over delta E. Now, if we go back to our formula of E is equal to mc delta T, and we rearrange it to make C the subject, we're going to get C is equal to E over m delta T. Now, if you remember, for this experiment, the mass is 1 kilogram, and obviously if we multiply delta T by 1, it just disappears, and so we get C is equal to E over delta T. Now let's compare these two equations. Over here we've got C is equal to E over delta T, and here we've got the gradient is equal to delta T over E. What do you notice about them? They are the reciprocal of each other. They're just the same formula upside down. And so actually, how do we find our specific heat capacity from our gradient? We simply say that the specific heat capacity is equal to 1 divided by our gradient. Okay, so let's now actually look at a real example of this, how we're going to calculate this gradient and use it to determine our specific heat capacity. Well, the first thing we need to do in order to calculate our gradient is to draw ourselves a big old triangle on our line. You guys should be quite comfortable with doing this by now. It's not something you haven't done before. It's something you've done quite a few times. So biggest triangle we can possibly draw. We then need to use the scales to determine how much our energy has changed. So in the example that I'm giving here, if we look down at the bottom left-hand corner here, so down here, we can see that we are starting off at 1.7 kilojoules and we're ending up at 21.2 kilojoules. That's therefore a change of 19.5 kilojoules. We're now going to do the same thing on the y-axis. So in our experiment, in going from one point to another, we have increased from 23 degrees Celsius up to 51 degrees Celsius. Now that is a change of 28 degrees Celsius. So our triangle has a height of 28 degrees Celsius and a run or base of 19.5. So how are we going to use this? Well, we're going to use these values. We're going to use the formula gradient is equal to rise divided by run. Now in our case, the rise is 28, the run is not 19.5, remember, because our x-axis is in kilojoules, so we need to take that into consideration. And rather than substituting 19.5, I'm substituting 19,500. If we put that into our calculator, we're going to get a value of 0.00144. Now, on the previous slide, I explained why the gradient isn't the specific heat capacity. It's in fact actually 1 over the specific heat capacity. So what do I need to do to turn this gradient into specific heat capacity? I need to do 1 divided by that value. So I've got C is equal to 1 divided by the gradient. This is 1 divided by 0.00144, which is going to give me a value of 696 joules per kilogram degrees Celsius. So that is my final calculated specific heat capacity for my particular material. Now, like with the specific latent heat example I gave earlier on in this lesson, this is just an example. Your calculated value is going to be very different to this. I just wanted to give you an example of how you complete that calculation so you weren't having to do it completely blind. So what I would now want you to do is go through both of those practicals, watch the videos that Dr. Cook has produced, record all your data, plot your graph, and then do the analysis that I've just shown you how to do. You then need to submit your calculated values on the Microsoft form that I have put on the show my homework, and I can then look to see, make sure that you've understood and that you know what you're doing. Good luck.